introduction into thermodynamics and statistical mechanics. Many of these things we need to understand what really is going on in molecular dynamics and Monte Carlo simulations. So that's why we continue this. And probably it will be a bit longer today. We scheduled 1 hour, but probably I take a bit more than 1 hour, perhaps the whole morning. And then in the afternoon we continue with the introduction into molecular dynamics. So I derived already, so I tried to motivate this nice equation going back to Boltzmann's equation with the Boltzmann constant here. I did not give the value. Perhaps you know it's 1.38 something 10 to minus 19 joule per Kelvin. And as Guru already said, these SI units are not always the best choice for our purposes. I mean, the energy of a joule is pretty large compared to interaction energies between atoms. So it's very often more practical to use electron volts because, at least that's what I teach my students, all the energies we deal with are about 1 electron volt. So the defect energy of a vacancy is 1 or 2 electron volts. The line energy of dislocation is about an electron volt per Borges vector. I think the grain boundary energies are also in this range per square angstrom or so. So appropriate units often are easier than to estimate. And I will also, later on when I come to molecular dynamics, I will make a short estimate which perhaps teaches you something about orders of magnitude, which sometimes are important. On the other side, as Guru also said, it's very convenient to use scaled units for simulations and calculations. But you always should be aware in which order of magnitude you are. So whether you can compare energies, for example. A small energy is not a small energy. This tells nothing. It's small compared to something else. Yeah? So that's something I wanted to emphasize. Okay. Then I continue here to introduce other thermodynamic potentials. Again, it's perhaps a bit strange use of words. In thermodynamics, we call potentials all these different kinds of, say, equivalence to energy. Yeah? So internal energy is typically a potential energy, but free energy, Gibbs free energy, and so on. So that's why we use this term. I'm not sure whether it's adequate. So we already came across the internal energy. U, and we got this equation. It's delta Q, and delta Q is TdS minus PdV. So this equation tells you which variables I can vary to get the variation in du. Yeah? So small amounts in the entropy or small amounts in the volume. So we can say U is a function of entropy and volume. And especially in molecular dynamics simulation, if you don't do certain tricks, the energy is conserved. Yeah? So in simple MD, simple means basically that I cannot control the temperature. You know, if I have a phase transformation, for example, there's a latent heat which can be released or uptaken, which would change the internal energy. This is, in principle, not possible. And similar, we had the H, which I also introduced. It was plus or minus. I think it was plus, yeah. So H is a function of S and P. But again, it's experimentally normally not a good idea to try to control the entropy in a system. Yeah? Experimentally, what we do is to control the temperature. Yeah? Temperature and pressure, or sometimes temperature and volume. So we have to somehow get rid of this TdS term and get an SdT term, as you probably know. And equilibria in a closed system are controlled by the entropy because in a closed system, as I explained yesterday, the entropy is always increasing or at most staying constant. If it stays constant, nothing changes anymore, and then we are in what we call an equilibrium. So equals 0, and since it's increasing, S goes to a maximum. For given U and V, for example. So how can we control temperature instead of entropy? I mean, how do we experimentally control temperature? Very simple. You put your experiment into what we call a thermostat. Yeah? So some big volume in the simplest case, which takes up the energy coming out from the system if, for example, it undergoes a phase transformation or so. Yeah? And that's basically what we also do in this theory. So we consider two systems. Two thermodynamic systems, 1 and 2. Which are in contact. So they can exchange energy. Okay. This table is a bit too low, so I always have to go down to right. So then the total internal energy is U1 plus U2. Or other way around. The internal energy of the second system is the difference of the total energy minus that of the first system. And the number of possible configurations in any of these systems I want to call G of U. configurations. And then this G of U. So if you have 100 possibilities in one system, 100 possibilities in the other system, no, it's not correct. We have to multiply. And since these are a very large number of configurations, I mean, if you have a, I don't know, here's a room filled with gas, I don't know, 10 to 20 something molecules, the number of arrangements which are possible for all these 10 to 22 is astronomical. Yeah? So and this means, and that's behind all this statistical mechanics, that only very few possibilities have a non-neglectable probability. It has an extremely sharp maximum. I mean, basically that all the molecules are evenly distributed or so. Yeah? And this is the, if you take the product here, and here we can apply the product rule. So this is G2, dG1, du1, du1, plus, no minus, sorry, because the minus sign here, G1, dG2, respect to du, du1 again. So the du1 or du2 is minus du1. That's where this minus sign comes from. So if you put this equality to 0, you find that 1 over G1 dG1 du1 equals 1 over G2 and probably you know this 1 over x dx is d ln x. So we can write this d ln g1 over du equals d ln g2 over du2. And now the entropy. Is 1 or 2 is Boltzmann's constant times ln g1 or 2. Now with a plus sign because it's a number of possibilities. Yeah? It's a bit confusing, these minus or plus signs. Yeah? And you see this we can rewrite. This is the ln g1 And apart from the entropy, this means ds1 du1 equals ds2 du2. And that's how we can introduce temperature. I said that introducing temperature is the most difficult part of thermodynamics lectures also. Yeah? What we know from experience is that we bring two systems in contact, temperature is equilibrated. Yeah? So we can define the temperature just as this ratio here, ds, or this derivative, ds over du. And it's not a stupid definition, otherwise these clever people would not have taken it. So it's inverse temperature. The exclamation mark here. Yeah. So it's a derivative of entropy with temperature. We can check whether this is reasonable. I write down here the delta Q equals TdS. If you have no work involved, this is equal to du. So if you, what physicists like to do, but mathematicians, I think they get crazy. You can just divide T du ds. Yeah, so that's, well, I put it in quotation marks. That's a simple derivation of this long chain of thoughts I brought before. Yeah. So, and now how to get temperature fixed. Now we are simple, or we are nearly done. We just use a very big system, U2, and a small system, U1. Thermostat. Often this is also called a heat bath, this thermostat. So, and here. I mean, any experimentalist knows how to do that. Yeah? The system has to be large, the system 2, so that any heat flux from system 1 into system 2 does not or only negligibly change the temperature there, or the internal energy there. So we can treat this big system. Also, maybe I should make this little note here. Which, if we reach equilibrium, goes to a constant entropy, to a maximum of entropy. I changed my notation here, so I think I should use a 0 here. And this is ds1 plus any temperature, any heat transfer from system 1 to 2. So this is entropy change. And that's a heat flux in or out, out system 1. And this corresponds to a change in internal energy. And since our temperature in system 1 and 2 is the same, this means ds1 minus du over T, 1 or 2. This has to be 0 here. So we come to the conclusion. We bring the T to the entropy, that T ds1, well, let's put it this way, becomes 0 in equilibrium. And that's, I mean, this probably is known to many of you. This is what we call the free energy, or the differential of the free energy. Yeah? So we introduce a function f equals u minus t times s, and df becomes 0 in equilibrium at a given temperature. That's what we control with our thermostat, and volume. And now is a question which I don't want to discuss here, but I guess you know, does it go to a minimum or a maximum? It goes to a minimum. I guess you all know This is what we typically learn. Free energy is minimized, yeah, in equilibrium. Free energy, F, is minimized in equilibrium. By the way, I guess most of you already know free energy, even this equation here. But do you know why it is called free energy? What is free about this energy? Does anybody know? That's also the origin, how these concepts were developed. Yeah, it's the same. Basically, it's a part of energy which you can convert into mechanical work or usable energy. Yeah? So probably you know that for heat engines, there's a maximum of efficiency, which is limited by this Carnot efficiency. And this is based on the free energy, and the rest is dissipated as waste heat. Yeah? And the higher the temperature difference between or during the process, the higher this efficiency. Yeah? But this is why it is called free energy. That's the part we can spend, and the rest we have to leave somewhere. I don't know whether you followed in the newspapers. In France, not in Germany, they have a problem with their nuclear power plants because such a nuclear power plant operates at an efficiency of roughly 30% or so, maybe 40%, but I think it's below. And the rest has to go into the rivers. Yeah, and if the rivers, as it was the case in the summer in Europe, dry out, there's no cooling, and you have to shut down this power plant. So that's the free energy. And same, by the way, for electrochemical processes. Yeah? In electrochemical processes, say in a reaction in a battery or so, yeah? You have some reacting species. There's an energy difference, but only the free energy can be converted into electricity. The rest is again somehow wasted.
Whether that entropy is thermal or configuration or both?
That's any entropy. I don't care what type of entropy it is.
Well, with taking the equation, can we consider the both or individually?
Here I did not. It's just the entropy which counts the number of possibilities. And now if you look closer, what are the possibilities? If, as we did, or Guru did yesterday, if we consider a fixed lattice, a rigid lattice, then you have so many possibilities to put your atoms on the lattice. This is what we call configurational entropy. But then if we deviate from this rigid lattice to, say, a vibrating system at finer temperature, then besides this configurational entropy, we also have this vibrational entropy. So we don't know precisely where the atoms are located. They slightly vibrate around the rest position. Yeah? So, but all this together gives the entropy. And here we did not care what parts of the entropy. And there are more contributions to entropy. For example, that's a bit tricky. In a metal, you have free electrons. And they also should contribute a huge amount of entropy, but that's not the case. But I don't want to go into all these details, so we don't have to care for that. So I can make it a bit shorter here. This df TdS minus PdV or plus PdV. I always forget. Minus T becomes, now if you take this differential of the product, this term cancels out, so this becomes S dt minus P dV. And that's what we wanted to have, a function which depends on temperature and volume. And similarly, as we did yesterday, we can also switch from volume to pressure as a free variable. Then we get the Gibbs free energy. If I want to replace volume as a free variable with pressure, I have to add PdV, P times V. So this equals SdT minus PdV plus PdV plus V dP. This cancels out, and we get so a function which is controlled by temperature and pressure, and this parenthesis here we call the Gibbs free energy. Or in analogy to before we called it enthalpy, this corresponding quantity, it's also often called free enthalpy. Yeah, I have some extra remarks here, but I think I skipped them. There are lots of games playing with these differentials. You can derive, if you take the second derivative, you can derive strange relations between thermodynamic quantities. If you take the second derivative here, then these are coefficients like the specific heat, du or dH, dt, or other coefficient of thermal expansion. This is also a derivative of something, and so on. This here means, let's just stay here. I can show one line here. So if we have this G dG equals S dt plus V dP. From calculus, you know that dg is just dg, if g is a function of t and p, dt plus dg dp. Yeah, that's just the definition of such a total differential. And this means that S is dg dt and V is dg dp. I think somewhere I lost the minus sign. Oh yeah, here, yeah, you're right. And already above here. I think it's also here. I wanted to emphasize a point which I could not explain here with this missing minus sign. So from this line, just by comparison, you see that dg dt equals minus S. Yeah? So the free energy as a function of time. S is a positive quantity, is entropy. as a falling function. Yeah? And if you sketch this, you get something like this. And now let's assume that you have different phases. Yeah? For example, a solid phase and a liquid phase. Just by intuition, we can assume that a solid has a low entropy. It's quite well ordered, while a liquid has a higher entropy. Yeah? If it has a higher entropy, this means that the slope for the liquid phase is steeper than for a solid phase. Yeah? So this means, oops. So for example here, this might be a solid. No, sorry, this might be a solid, the red one, and the green one is a liquid. Yeah? And now if we say under our conditions with constant pressure and constant temperature, or if we vary the temperature slowly, we have to minimize the free enthalpy. Yeah? This means for temperatures to the left of this intersection point, we have this stable phase, and to the right, we have that stable phase. I need another color here. So we have here a solid phase, and here we have a liquid phase, and we have the melting temperature here. Just without knowing anything about the system, just by saying, okay, the entropy of this phase has to be larger than the entropy of that phase. Slope is steeper, and then there must be an intersection point somewhere. Yeah? This already explains, I don't know whether you ever thought about it, why we always have this sequence with raising temperature. We go from a well-ordered state to a less ordered state, so solid, liquid, gas. Yeah? Or if you have an ordering system like the one we showed yesterday, at low temperature things are ordered, at higher temperature things are disordered. And sometimes it even helps to intuitively say the direction of a chemical reaction. Yeah? If you have one gas phase on the right side, you have one mole of gas on the right side, you have only you have 2 moles of gas on the right side, you have 1 mole of gas phase on the left side. Then you can predict that at high temperature the equilibrium will go to the right side where you have 2 moles of gas, 2 molecules of gas, because there you have the higher entropy. So this is often helpful to intuitively predict behavior. Okay, so next step is until here we assumed that the composition of our system is given, or that we have just one species. We did not distinguish between species. But of course, it's not the most interesting case in metallurgy. We always deal with alloys, so at least you have 2. In technical alloys, you often have much more than 2 components. So systems with variable composition. This sounds more complicated as it is, at least here on paper or on this screen. What does it mean if you have, say, a piece of copper with some aluminum in it, or a piece of aluminum with some copper in it? We have a further variable to characterize our system. Yeah? Instead of saying we have 1 liter of aluminum, we have to say we have now 1 liter of aluminum containing so many % of copper. So that's another state variable. And yeah, for the beginning, I start just with a number of A atoms, B atoms, and could be more. And this means, I'm not sure whether always, but for the moment I will stay with the free enthalpy or Gibbs free energy in my arguments. It's the same for the free energy. In principle, it does not matter. So then we have the G of T, P as before, and now these numbers NA, NB. Which give our system. And if we write down the differential of this, so how does it change? As before, we get the VdP minus SdT plus, now we can vary the number of A atoms, the number of B atoms, and for this purpose, we have to take the derivative one has to be a bit careful, but that's what we learn, or what you hopefully learned in calculus. Of course, these partial differentials are taken where all the other quantities are constant. So this is at constant P, constant temperature, and constant number of B atoms, and so on. And this derivative gets its own name. We call it, for some, I don't know, historical reasons, the chemical potential. As I said, this term potential appears in different occasions here in thermodynamics. The chemical potential has not much to do with the thermodynamic potentials I just discussed before. So we call this mu A and mu B. Chemical potential of species A and B. There's one weak point, not very weak. N is an integer number, so many atoms. So how do we take the derivative with respect to an integer number? Yeah? But since normally we are dealing with large number of atoms, nobody cares for that. So. And I don't want to go into this. But more precisely, what does it mean? Again, if you look at this differential, this gives how much does the free enthalpy change if I change the pressure by a certain amount, so on. And this tells you how much does the free energy change if I add an A atom to my system. Here, how much does this, the free enthalpy change if I add a B atom? Yeah? So it's just the change by adding one A or one B atom. This intuitive view, you should, if you don't know it already, you should try to bear in mind. Yeah?
Freddie, I had a point. If some of them are from mechanical engineering background,
Yeah.
so they might have done variational calculus.
Okay.
They might also know with constraint how to do variation and Lagrange multiplier.
Okay.
And we can think of all these quantities like mu, t, etc. as the Lagrange multipliers associated with minimization of energy while keeping the other quantity constant.
Right.
So you can think of temperature as minimization of entropy, keeping the energy constant. Similarly, you can think of minimization of energy, keeping the number of atoms constant. Then that will give you a Lagrange multiplier, which is the chemical potential, and for volume it is the pressure. So that is another way to think about some of these quantities, because some of you are from mechanical engineering.
I think at some point we come to these Lagrange multipliers when I introduce the Boltzmann probability. So we also need the Lagrange multipliers. But here, I mean, I would propose, think of the chemical potential just as the amount of free enthalpy you add to the system if you put one additional B atom into it. And this also leads to this, and I think I once gave a lecture on solid state physics. I introduced the Fermi level just as the maximum energy up to which energy states are filled. Yeah. But of course, if you add one, you have to add this Fermi energy to the system. So that's basically the same. And you can introduce it rather abstractly and get the temperature dependence of the Fermi energy. And I think the chemical potential of the electrons is not precisely, it's only at 0 Kelvin the same as the Fermi energy. So there are subtle differences. Yeah. So, but I mean, I'm not so much going into these mathematical details. Yeah. What do we get if we keep the total number of atoms constant? Then we get an extra condition. This means, like in the situation Guru showed yesterday, he did it for a magnetic system where the spins can flip, but in alloys, as we will see later in the Monte Carlo simulation, we often just use a constant number of atoms but allow them to change from a copper into a zinc atom or vice versa. Yeah? So such a condition here. And if we introduce such a condition, this means that dNA, so the derivative of a constant is 0, equals minus dNB. And this now means our GG, to save some writing, I put pressure and temperature constant here. So if I put pressure constant, this is 0. If I put temperature constant, this is 0. Then our dG becomes mu A dNA minus mu B dNA, which means mu A minus mu B. dNA. And this means for equilibrium, where dG is 0, the product is 0 if one of the factors is 0. This is not 0, so this has to be 0. What does it mean? If you bring two systems in contact and they can exchange atoms, they do it until the chemical potentials of both sides are equal. Yeah? And at some point you probably learned that we have diffusion if concentrations are different. Yeah? So you take two two pieces, a piece of copper with 10% of aluminum and a piece of copper with 5% of aluminum, then according to what you perhaps learned, aluminum will diffuse until you have everywhere 77.5%. But that's not necessarily true. Yeah? I mean, very often, for example, if you form precipitates, diffusion does not go until everything is homogeneous, all concentrations are equal. But diffusion goes until chemical potentials are equal. Yeah? And I mean, this is obvious from this equation, but what does it mean? It means if I have two systems in contact, I move one atom from one side to the other side. This gives me some amount of energy. Yeah? I move it to the other side. This gives me another amount of energy. Yeah? And in equilibrium, since the chemical potentials then are equal, they just hop back and forth without changing the energy. Yeah? So this equality of chemical potentials is more important than the equality of concentrations. It's only because, I mean, it works in many cases, it's because chemical potential is, what is it called? Not homogeneous, but function of concentration. Yeah. Normally it's just a logarithm of concentration. Yeah. So, but not in all cases. Yeah. So.
That is why it is also called as diffusion potentials.
Yes. Yeah.
And this also is why when you put two semiconductors on this thing, they say that Fermi levels have
right.
to equalize.
Yeah. So this is behind semiconductor technology, the p-n junction, for example. Perhaps you know electrons or holes flow from one side to the other side and create this space charge region and so on, which is responsible for all these nice properties we obtain. Yeah? And this is in a p-doped semiconductor, you have a higher concentration of holes, a lower concentration of electrons, and on an n-doped semiconductor, vice versa. So electrons will flow from one side to the other side to equilibrate the Fermi levels. But that's another application of the same ideas. Yeah. But I'm not sure how far semiconductor physics applies real thermodynamics there.
Yeah, but all this is taught. They are told that okay, you put them together, the Fermi levels should become equal.
Yeah.
But this connection is never made that it's
right.
like chemical potential. That is
right. It's like diffusion. Yeah. I mean, I can give a simple example here. So what happens now if, say, mu A larger than B? If mu A is larger than mu B, this term here becomes negative. dg goes to a minimum, so also is negative, is falling function. So dNA must be positive. So no, I think I confused mu A. Yeah, this is positive. Then is dNA negative. Yeah. I was confused because in my notes I have it correctly. Minus, so I write it slowly here. It's positive, dg must be negative in order to go to equilibrium, and then dNA must be negative. So you reduce the number of A atoms. That's how you win energy. You take out A atoms from the system to reduce the energy, and vice versa. So that's why you get diffusion, for example. So what else do I have here? Perhaps we make a short break now because there's one chapter missing where we get the Boltzmann distribution, and I would like to make a short break. I will now go through a short example, which we then need. I thought I could skip this example, but we need the result of this example. So I just wanted to show a situation Guru already described yesterday. Let's assume we have a binary system on a rigid lattice. So we have a crystal like this. No. It's not very periodic, but anyhow. So we have A atoms and B atoms sitting on this crystal. This is a typical situation we have in simple Monte Carlo simulations. And we can try to calculate the number of possibilities of states here, number of configurations. Omega. Yeah, if we have so many red atoms, we just have to count the number of possibilities we have for the red atoms, the rest is blue. So we, if Na and Nb is the number of A atoms and B atoms on this lattice, the number of configurations is the binomial N over Nb, which is given, or which is a faculty N faculty divided by and for the entropy we need the logarithm. So that's logarithm of N faculty this. And here we can again apply Stirling's formula. I think we already did it yesterday. And here nature is very friendly, as we will see, or perhaps you know that these second terms all cancel out. It's not equal, it's approximate. Plus N minus Nb. And you see here minus N plus N plus Nb minus Nb, so these terms cancel out. And we can I'll write it here again, N minus ln N plus minus Nb ln Nb minus Of course, nobody speaks of a crystal containing 2 times 10 to 23 zinc atoms and 8 10 to 23 copper atoms, but we speak of concentrations or molar fractions or whatever. So we introduce our nu B equal NB over N and NA, which I don't use here. So we take out the N here. And now we want to have also here, oops, sorry, I made a mistake, this is NB. I want to translate this into nu B, which I did already in the, I can write this nu B, this NB as nu B times N. Yeah, and maybe I skip one intermediate step. This is N times nu B. This is NB here. And for the logarithm, we can split this up into a sum. And we can bring together all these ln n terms here. One, here we have minus nu B. Here we have minus 1 minus nu B. So this is very nice, it's 0. Plus, no, minus, sorry. And then the entropy, now we have the number of possibilities or the logarithm of this number. Entropy equals Boltzmann constant times this number here, logarithm of the number. Take out the minus sign. You see here are all minus. Here are minus signs. Yeah, here and here, minus n, and then we have nu b ln nu b plus 1 minus nu b ln 1 minus nu b. And here at this point, I used to ask my students, I told you that entropy is positive, but here we have a minus sign. How can this be? Did I make a mistake again, or why is this minus sign perhaps correct? Anybody sees? Yeah. This ln's here. there's a quantity smaller than 1, so this is negative, this is negative. So this entropy is indeed positive. And it's, by the way, this is probably you know, this ideal entropy of mixing. It's sometimes a good idea or a good exercise to take the derivative, how it depends on nu b. So it looks like this here. And the question is, what is the slope on the sides? I mean, you can do this. It's a simple calculation. I think you need L'Hopital's rule to get the derivative on the sides. And the answer is the slope here is infinite. Yeah? And this, in a way, explains why it is so difficult to get very pure materials. Yeah, I don't know whether you ever had to do with pure aluminum, pure copper, or whatever. You can pay enormous price for 3959 or so of these. So this 59 means 99.999% purity plus some extra. I think aluminum, typically the commercial aluminum is 99.5. So contains 0.5% of iron mostly and some other elements. So if you need for experiments 3, 4, 5, 9 aluminum, it's increasingly or exponentially increasing expensive. And this is because the entropy here is so steep. Yeah? So by adding very small amounts of these solute elements, you increase the entropy, so you gain a lot of entropy, which at finite temperature lowers the free energy or free enthalpy. And yeah, this somehow you have to fight in this purification routines. Yeah? While the energy in a similar approximation, the regular solution model has a normal slope here. It's more like a parabola with non-vertical slope here. But that's only a side remark. What I need in what's for the next chapter here is that very often we get expressions for the entropy which have a similar appearance here. Yeah?
Since this is the binary system, the entropy of mixing comes into the picture. What would be the case for pure substance?
For a pure substance, of course, this part is 0.
Okay, what would be the configurational entropy?
Yeah, this would be 0 if the crystal is really perfect and really pure. Yeah? And that's what I said. If you add very few solute atoms, you enormously increase, you go up here perpendicularly, you enormously increase the entropy. Yeah?
But vacancies do exist, right?
This is what I wanted to say. That's the next, in quotation mark, impurity, that you also, you can play the same game for vacancies, and you end up with a relation that the concentration of vacancies follows a law exponential minus the formation energy of a vacancy over kT. Yeah? And this is because you have also these large contributions to entropy by vacancies. As Guru said, and I come back to this, typical vacancy concentration of most metals at the melting point is about 10 to minus 4, perhaps 10 to minus 5, because you have this entropy. But of course, if you go to lower temperature, entropy plays a less important role, and then the contribution gets smaller. There are substances, but this has other reasons, which have much higher concentration of vacancies. And that's technically important. I mean, you can go up to 0% of vacancies in certain, I think it's not in metals, but in ionic crystals. One example is zirconium oxide doped with yttrium oxide. Yeah? This is what is used in fuel cells and the lambda probe, perhaps you know from cars, yeah, to measure the oxygen content. So by adding an element with another valency, you have to compensate this with oxygen vacancies. That's not an entropy, but an energy argument there. Yeah, the entropy of an ideal gas has a similar appearance. Yeah. So I think instead of the concentrations, you have the partial pressures here. So that's why I love this system, this ideal solution model here. That's what we call the ideal solution, where you just consider the number of possibilities, which is very simple here. I mean, you all followed the calculation. And for an ideal gas, the calculation is much more complicated, because how do we count the number of possibilities for a gas molecule, yeah, or for a number of gas molecules? Classically, one would say they have infinite number of possibilities.
But that comes from energy part, right?
No, this comes from quantum mechanics, that then in phase space is the space spanned by the spatial coordinates plus the velocity coordinates. In phase space, or momentum coordinates, in phase space you have finite volumina given by the uncertainty relation. Yeah? So if you want to define or want to know the location of a molecule precisely, quantum mechanically it's not possible, because this would mean that you get infinite momentum. Vice versa, if you measure the velocity precisely, you get delocalization. Yeah? So there's an optimum, yeah? And that's what is called the phase space volume. And then you can count the number of possibilities, like I did it here on the lattice. But as I said, it requires much more background, and here it's more a kindergarten model, but the result is more or less the same.
What happens in liquids?
I don't know.
Cannot be neither the phase space argument nor a
I think you have to also consider
Go
phase
to phase
space.
space
Yeah,
and
I
something
guess so.
similar,
Yeah. I think there is nothing like an ideal liquid. I think there are, I tried it once, ideal solution models for liquids. I mean, if you put small amounts of salt into water, this you can treat. Yeah, I think then it's more like an ideal gas, ideal solution. There was also the point I mean, I'm deviating, but I came across, and I really don't understand it completely. The solubility of gases decreases with temperature normally. I mean, normally solubility in solids or in liquids increases with temperature. Yeah? I mean, if you have hot coffee, you can put more sugar into it as with cold coffee. But gases behaves inversely. Yeah? And I looked it up already a couple of times, but I'm not sure as I understood it. So everybody knows it. I mean, if you boil water, it starts to make some noise right before it starts to boil. These are the dissolved gases which are released. Yeah? Okay, the world is more complicated as we expect. So, but this is not what I want to use here. I just wanted to make the statement that very often we have relations for the entropy like this here. So if we have certain subsystems, then we get an entropy minus n kb sum pi ln pi. The pi is just the probability to find the system in one of these subsystems. So if we take the concentration here, this would be that the atom is a B atom. Yeah? probability. Ni atoms are found in subsystem I. And that's a point which everybody knows, but few know where it comes from. We are often interested, what is the probability that a part of the system has an energy higher than the average energy? Yeah? This is what is, for example, needed for diffusion. Yeah? We have all our atoms. They are more or less sitting in potential minima. And once in a while, an atom jumps to a neighboring site if there is a vacant site or so. Yeah? So, and what's the probability that this special atom acquires sufficient energy to overcome barriers around it? Yeah? That's the so-called Boltzmann probability, which I sketch the derivation here. That's a question I want to answer. I guess you know the answer. Above the average energy U. I call it U bar. And that's what is behind all these considerations of fluctuations and so on. And it's also more or less behind this probability to find a vacancy. What's the probability that one atom just leaves the crystal spontaneously, so to say, yeah? So that we obtain a vacancy. And this is obtained if we take this equation from before. We just take the entropy per atom or per subsystem, 1 over n. I mean, I speak of subsystems, but basically I mean single atoms for our case here. Yeah? I mean, in principle, of course, it's more general, but for our purpose, it's just the single atoms. This entropy has to be maximized in a closed system under certain conditions.